Okay, so so FTLI 3. The idea here is, I mean, obviously we're going to use the fundamental thermal line integrals. We're hoping to use the fundamental thermal line integrals. But the hard part of this problem, I don't know. It looks like the hard part of this problem might well be that I got to figure out what my curve is. Right? I've got the intersection of these things. So what in the world does this look like? Well, notice that our first planes, so I've got x equals y, and I've got y equals z. In other words, x, y, and z are all the same thing on the line that I'm looking at. So in other words, I'm going to be moving in the direction of the vector 1, 1, 1. So I'm not even going to draw the planes themselves. I'm just going to say, well, look, 1, 1, 1 maybe goes in that direction. And so I'm looking sort of along this dotted line. That's the line described by those two equations. In fact,
what plane is that dotted line?
Well, this dotted line is in both of these planes. I claim that this dotted line is the intersection of these two planes.
Oh, is it going along the 1, 1, 1?
Yeah, that's right. It's going 1, 1, 1 is sort of the direction vector for that dotted line. Does that make sense? Mm-hmm. Yeah. In fact, you can view this as being the symmetric equations for that line, as it turns out. So let's see here. Now what? Okay, well, I want to know the intersection of these two planes. Namely, I want to know the intersection of this line with this sphere, x squared plus y squared plus z squared equals 12. Now there's a sphere here, something like that maybe. Hard to draw. And algebraically, I want to know. I mean, ultimately, what I've got then is a line segment that goes from there to there. So this is my curve. It's a line segment like that, oriented. Let's see here, oriented in the direction with y increasing. So oriented, yeah, good, in that direction. Does that make sense?
No. Why is it just a line?
Start, end. Because these two planes intersect to make a line, this dotted line, and I want to know how that line intersects with this solid ball. I said sphere. I meant ball. Excuse me.
So. What I did was when I took x equals y, I just took that as it's
a plane.
I went into the xy plane and drew that line.
Right.
And then the y equals z in the xz plane and drew that line.
Right.
And then if you drew the ball over that, I took the 2 points at the head of the two vectors and kind of connected it.
That just doesn't work. I mean, so let me see if I understood you correctly. So it sounds like you drew this line in the xy plane,
right?
And then you drew sort of this line in the yz plane,
right?
And then you looked at these vectors themselves.
Correct.
So that's not really, I mean, the reason this doesn't work is because we're not actually interested in that line. What we're interested in is the plane that's defined by that line, right? When you write down x equals y, sure, that line is what that looks like in the xy plane, but but this is actually the equation of a plane, right. And I'm interested in the plane itself. Yeah. Does that make sense?
Yeah.
Yeah.
I think I'm getting that.
Yeah. Okay. Yeah. Cool. No worries. So yeah, the geometry of this is probably the hardest part of the problem. Is figuring out what in the world am I supposed to do with this, and conveniently, this gives you symmetric equations. And by the way, as symmetric equations, you could rewrite this as, x minus 0 over 1 equals y minus 0 over 1 equals z minus 0 over 1. And so this in this form suggests that you've got a point that goes through the origin, 0, 0, 0, with direction vector 1, 1, 1. Does that make sense? Okay, so we've got this line segment. Are you good with this line segment now? Okay. All right, so we've got a very clearly defined curve now. We've got a vector field. We want to compute a line integral. By the way, you can parameterize that curve without too much trouble. But then you're going to deal with this vector field, which looks pretty nasty. So let's see if we can outsmart the problem. Let's see if we can use the fundamental thermal line integrals. I would need to find an anti-gradient for this vector field, and let's play that game. Our vector field is y cosine xy plus z squared x cosine xy, and then let's see, 2xz. So we're going to play the anti-gradient game, and I claim that f is going to have to equal each of the following three things. I'm going to take the x antipartial of that, the y antipartial of that, z antipartial of that. So I claim that I get sine xy plus xz squared plus unknown function of y and z. Then I get sine xy. Okay, that's cool. That's good news. And then plus unknown function of x and z. And then here I get, let's see, the z antipartial of that is xz squared. Cool, right? Lucky break. Plus unknown function of x and y. And now, is there a function that satisfies all three of these equations? And I claim that, yeah, sure there is. You can mix and match and see what goes where. And, well, I claim that sine xy plus xz squared satisfies all three of those equations. In this equation, that function is just 0. Right? In this equation, that function ends up being xz squared, and that's cool. That's fine. It's allowed to be xz squared. And in here, this function ends up being sine xy, and that's also perfectly fine. Everybody happy? So we've got a curve. We have an anti-gradient, and so I can compute the line integral over that curve f dot dx as little f here of b minus little f of a. Now you just got to figure out what a and b are.
That's what I was having trouble with.
Oh, okay. I'm sorry. I misunderstood. I didn't realize. So, all right. Let's talk about this point here. What can I decide about that point? Well, I know that x is equal to y. I know that y is equal to z, and I know that x squared plus y squared plus z squared is equal to 12. Well, if x, y, and z are all the same thing, that gives me 3x squared is equal to 12. So x squared is equal to 4, and x is plus or minus 2. Does that make sense? Yeah. So it will, now, of course, x is plus 2 for this one, and it's minus 2 for this one.
I got that answer.
Yeah.
But with my image, I was just like, that can't be right.
Yeah, you couldn't drive it with your picture.
Right.
Yeah, okay.
So
That makes sense.
thing, I just couldn't.
I see. Okay. Well, then, yeah, you had part of it right. Yeah. Right. Is everybody happy? So the point is, so if you know x, then, of course, y and z are the same thing. So these these 2 points here are f of 2, 2, 2, and negative 2, negative 2, negative 2. And that's just plugging in at this point. Okay. Let's see here.